Hello folks, in this video we will talk mainly about vector spaces. However, there is a section we didn't have time to cover in the previous recording, so we'll start with this. It's a very small section. It is a section on matrix norms, and then once we complete that we'll move on to the next chapter actually, which is on vector spaces. So matrix norms, first of all, what is a matrix norm? I think it will come as little surprise to you if I tell you that it is a norm for matrices. It is an operation like this. You give it a matrix and it gives you back a number. In a way, you can say that it measures how quote-unquote big the matrix is. I'll say more about this later. It needs to satisfy three properties. It needs actually to satisfy the same three properties as a vector norm. So the first one is that the norm of the matrix A must be non-negative. It can be positive or it can be zero. It cannot be negative. Well, it's positive actually most of the time. The only way for the norm of a matrix to be zero is if A is the zero matrix. I'll write this down here. The norm of the zero matrix is 0, the number. This is a matrix. This 0 is a number. Second property, if you scale your matrix A, if you do something like A, a number, times big A, which is a matrix, then you can take A outside, like this. This is the absolute value of A, times the norm of the matrix A. For example, the norm of 2A is twice the norm of A. The norm of minus 5A is 5 times the norm of A. Simple as that. And last one is the triangle inequality. We didn't dwell too much on that when we discussed about vectors. We will not discuss much about this here either, because it's not that it's not important, it's that we will not need it much. So this is called the triangle inequality, and similar to the case of vectors, we have that the norm of A plus B is less than or equal the norm of A plus the norm of B. We are allowed to talk about the norm of a rectangular matrix, which is M by N, but as I have written here, we will focus on square matrices, n by n. So here on this slide, I have assumed that A is a square matrix, n by n. And I'm saying, if I give you a norm, a vector norm on Rn, can you construct a matrix norm? And the answer is yes. Given a vector norm, we can construct a matrix norm. This is known as the induced norm. Don't look at the formula. I want to explain this to you mainly. Take a vector x, and then you multiply this vector by a. So you get the vector, again, ax. I'm asking how larger ax is compared to x. Is it double the size? Is it triple the size? Is it perhaps half the size? So I'm asking how ax, the length, the norm of ax, compares to x. And of course, if you give different vectors x, you will end up with a different ratio. So perhaps along this direction, ax kind of magnifies, increases the length of the vector. If I take this different direction, maybe ax shrinks the length of the vector. Ax reduces the size of the vector. So I'm asking then, what is the largest ratio I can achieve by multiplying by a? So what is the most this matrix A can do? Can it double? Can it triple? Can it quadruple my vector? So I'm looking for the maximum. Here I have written SUP, supremum, but think of it for now as maximum. I'm now realizing that actually we will define this later in the module. Think of it simply as the maximum of this ratio, of this magnification, this scaling factor. And of course, I've written here that x is not equal to 0. I don't want you to remember this formula. I'm just telling you how, given a vector norm, you can construct a matrix norm, the corresponding matrix norm. And the main point I want to make here is the following. I've listed a few things here, but I want your attention only on the first line. A famous, super famous norm of vectors, a famous vector norm, is the Euclidean norm. This thing here, you see, is the famous Euclidean norm, right? If you take the Euclidean norm and you use it to construct a matrix norm, you have the, guess what? You have the Euclidean matrix norm. The Euclidean matrix norm. What is that? Have a look. Let me remind you, the Euclidean norm of a vector is the square root of x transpose x. The Euclidean norm of a matrix is the square root of the minimum eigenvalue of A transpose A. Let's break it down. A is a matrix which is n by n. A is n by n. The matrix A transpose A is, guess what? It's a matrix n by n. And it's not very difficult to see that A transpose A is symmetric. A transpose A belongs to the set of symmetric matrices, which we denoted like this, S, blackboard style, to the power n. This is a symmetric matrix, and if you remember, we said that symmetric matrices have real eigenvalues. I'm emphasizing this because the eigenvalues of a matrix in principle can be complex as well. But no, this is a symmetric matrix, so it has real eigenvalues. Since they are real, they're on the real line, they are like this, lambda 1, lambda 2, and so on. Lambda, how many? N. It is an n by n matrix, it has n eigenvalues. Right. So there is the smallest one, then the one after that, and so on, and the largest one. I'm taking the smallest one. This is the minimum, the smallest eigenvalue of A transpose A. This is the Euclidean norm of a matrix. So whenever you see this, whenever you see norm of A subscript 2, this is the Euclidean norm, and it is the square root of the minimum eigenvalue of A transpose A. This is important. This is something you need to remember. So when it comes to vector norms, you need to remember this famous vector norm, the Euclidean norm. When it comes to matrix norms, you need to remember this famous matrix norm, the Euclidean matrix norm. I'm repeating the same time again and again because it's very important. There are some other norms like the 1 norm, the infinity norm, and so on. And they have their corresponding matrix norms. If you want, have a look, but it's not absolutely necessary. If you're curious, of course, that's why I listed these things here. There is a norm, actually there are many norms that we can define for matrices, like this one you see over here. It is quite a natural definition, the square root of the summation of the squares of all the elements of the matrix. This is called the Frobenius norm. Frobenius, like this. And this comes from no matrix norm. This is not an induced matrix norm. We cannot find a norm, a vector norm that induces this particular norm. So it doesn't come from this formula. Okay, so let's move on. If now I have an induced norm, this comes with an advantage. It lends itself to this beautiful inequality. So the norm of ax, a and x are together, they multiply each other inside the norm, is less than or equal the norm of a times the norm of x. For example, if you use the 2 norm, we know that the 2 norm induces a matrix norm, then the Euclidean norm of ax is less than or equal the Euclidean norm of a times the Euclidean norm of x. You can't put any norm you like there, it must be a pair of a vector norm and the corresponding matrix norm, the corresponding induced norm. Moreover, you have this property. The norm of a times b is less than or equal the norm of a times the norm of b. But this is enough about matrix norms. I want us now to move on to the next part, which is vector spaces, which is a very interesting topic. We will start with the basics, well, definitions. Let's focus on Rn, the set of all vectors of dimension n. And I'm asking, on that space, what can we do? So on that space we have vectors. What can we do with these vectors? We can add them. You have v1, you have v2. You can do v1 plus v2. Have a look. This is the whole Rn. Think of r squared, actually. 2-dimensional only. So it's a huge, endless, flat surface. Let's say 0 is over here. And you have this vector v1, and you have this vector v2. What can you do with these vectors? Well, you can add them. You can get this vector v1 plus v2. And guess what? This is inside the space. So addition doesn't do anything weird. The sum of 2 vectors is a vector. I'm stating something super obvious here. Or take this vector, let's call it w. Let's not call everything v, just for variety. And here you have 2 times w. And now here you have 3 times w, and so on. 2 times w, 3 times w, a million times w is again a vector. So these are 2 things we can do with vectors. And when we focus on the operations of vector addition and scalar multiplication, then these operations satisfy 8 properties. They're really trivial, almost unworthy going through them. I'll do it very quickly. So whether you do v1 plus v2 is the same as v2 plus v1. Well, okay. When you have 3 vectors and you want to add them, you want to do v1 plus v2 plus v3, you can add v2 plus v3 first and then add v1, or you can add v1 plus v2 and then add v3. Well, all the rest actually are like this. They're nothing extremely complicated or unexpected. Like look at number 5. 1 times v is equal to v. So to put it simply, vector addition and scalar multiplication satisfy a bunch of obvious properties. And the question now I will ask is, I'll say we can do this in Rn, we can do this with vectors. Can we do this with other things except vectors? Are there other spaces where we can do analogous things? And there are. Let me give you a very strange, peculiar, exotic example. So take this space, which is denoted by C01. What is this? This is the space of continuous functions. So now my v's are functions. V is a function from the interval 0, 1 that gives me a number. What can we do with these functions? We can add them, and the result is a function which is again continuous and defined on 0, 1. All right, and we can multiply them by numbers. So if v is a continuous function, then 2 times v, 3 times v, minus 20 times v is again a function, a continuous function that is defined on 0, 1. So it seems that we can do on this set, on this space, we can do on C01 things that we can also do with vectors in Rn. So there is some affinity between the two. This means that we can treat continuous functions, we can treat all the continuous functions as if they were vectors. You know what? We can call them vectors, actually. And let's take it a step further. Are there any more spaces like this? There are. You know, the set of real numbers is an example. The Euclidean space Rn, the set of vectors. But also, the set of matrices is like this. Yes, we can treat matrices as if they were vectors. In what sense? We can add them and we can multiply them by numbers. So, if A and B are matrices, say 5 by 5, then A plus B, I can do that, and this is a matrix, and I can do C times A, and this is a matrix again, and these operations of addition and scalar multiplication satisfy these 8 very simple trivial properties. I can do this with functions, as we discussed before. I can do this with polynomials. Yes, I can. So if P and Q are polynomials, then P plus Q is a polynomial, and then C times P is a polynomial. And even if you take, let's say, polynomials of degree up to 2, this is again an example where we can treat the elements of this space as if they were vectors. And these sets are called vector spaces. So whenever we talk about vector spaces, I want you to think of Rn. When we say this is a vector space, we're actually saying something extremely simple. We're saying that treat the elements of this space, treat the polynomials, the continuous functions, the matrices, treat them as if they were vectors, common, ordinary, everyday, mundane vectors of Rn. So let's give the definition. What is a vector space? So a vector space, here is the definition, a vector space, or if you want the full name and surname, a vector space over R, or a real vector space, is a set V, as in vector, equipped with, which comes with addition, plus, and scalar multiplication, dot, you can multiply a number by a vector, that satisfy, these operations satisfy the 8 properties we mentioned earlier. For completeness, here are the properties. But really, I find it a little boring to go through these 8 properties because they are kind of the things that addition and scalar multiplication satisfy when we study Rn. So think of Rn. Now, we have vector spaces, and we should think of vector spaces like endless planes, or endless, perhaps 3-dimensional spaces, if you prefer, but they extend in all directions. Usually we sketch them like a box, but imagine they extend towards infinity, so to speak. A subspace here on this vector space, let's say that this is V, this is my vector space. A subspace, here is 0, looks like this, looks like a line in a 2-dimensional space. Or if you go to a 3-dimensional space, a subspace looks like a line, can be a line again, that runs through 0, it must run through 0. Or it can be a surface, a flat surface that goes through 0. So let's give now the definition. This is the geometric understanding, which I think is a lot more valuable than what I will read out to you now. So this is a subspace. U is a subspace of V, and also this subspace extends and it has no limits. Let's read the definition actually. We say that the set U is a subspace of V if I take 2 elements inside there. If I take a U1 and I take a U2, and whenever I add U1 plus U2, these are inside U. Indeed, you see here, if you do U1 plus U2, the result is inside U. It is not here. You will not get something like this. Also, if you multiply U, this is not a very good sketch, I'll do it again, sorry, just give me a second. So this is 0, this is my subspace. If I take a vector, let's call it now V, and V is inside my set U, and then I take 3 times V. 3 times V is again the set inside the set U. So this is a subspace. This holds. For example, 3 times U1 plus 5 times U2 is again inside my subspace. Or even U1 plus U2 is inside my subspace. U1 minus U2 is inside my subspace. For whatever numbers lambda 1 and lambda 2 you put there, lambda 1 U1 plus lambda 2 U2 will again not escape the subspace. It is really a simple concept. I'll give you an example, a very simple example. In Rn, take a vector x, take it just not to be 0, and define this set U, which is the set of lambda times x, where lambda is a number. So this set U contains things like, this set U contains things like x, of course, it contains 2x, it contains, this symbol means contains, it's like belongs to but turned not upside down, like this. This means contains 2x, contains minus 3000 times x. This U contains 100 times x, and so on. So how does this U look like geometrically? This is my space V, my vector space. This is 0. And this is my vector x. Now have a look. This set U is this. It is the line that supports, as we say, my vector x. I'll move this here. There, you can see it there. So this is an example of a vector space. So this concludes the first section in our discussion about vector spaces. We gave the definition of a vector space. It's a set where we have an addition and a multiplication that pretty much behaves like Rn. And we can define subspaces. The subspaces we just defined are vector spaces themselves. So I can focus my attention on U, and this U again, you know what? This U behaves like Rn again. Why? Because I can take elements of U, I can add them, and they are still inside U. I can multiply them by numbers, and they are still inside U. So this is the concept. Now I want to give you another couple of definitions. One is span, and the other is the definition of linear independence. You might have heard of both of these things. So first of all, what is a span? I'm giving you a set A, big A, like this over here, A. And this set is inside the vector space. We can define the span of A to be the set of all combinations, I'm combining here, all combinations or all linear combinations, as we say, of A1, A2, A3 up to AK, where these A1 up to AK are taken from the set A. These are taken from the set A. I know you might find this a little convoluted, but I will give you an example. To put it simply in words without the equation, so this equation you see here says the same story as the sentence right below. The span of A is the set of all vectors that have the form lambda 1 A1 plus lambda 2 A2 plus and so on and so forth up to lambda k AK, What is K? Whatever you like. You can take 3 of the vectors inside A, 4, 5, 6, and so on. The span of a set A is a subspace of V. This is a little all too abstract. Now, I think the sketch that I'll make will make it super clear. So we have this vector space V. I think there is a bit of a delay, but I hope we can deal with this. So we have this set V, which is a vector space, and I'm taking just one vector, just one. I'm taking this vector V, and I'm taking A, wait for it, and I'm taking A to be a set that contains nothing but V. It only contains one element, V, nothing else, just one. What is the span of A? What is the span of A? Well, the span of A is the line that supports V. The span of A is this orange line. Simple as that. This is the span of A. I'll give you another example where we will have, you guessed right, we will have 2 vectors. I'll take now V1 and V2. This is my vector space V, and I'm taking V1 and V2. You know what the span of A is a set that contains V1 plus V2, V1 plus 2 times V2, 3 times V1 plus 98 times V2, and so on. It is the set of all linear combinations of V1 and V2. And you know what that is really? Because I've made the sketch here 2-dimensional. This is the whole space, the way I have sketched it. I want to give you one more example. Let's have a look. I want to make some space here. Give me a second. Don't know why this doesn't work. I will delete it. I want to make another example here. I want to give you a 3-dimensional example. So you have this 3-dimensional space, 3-dimensional, and I want to take 2 vectors now. This vector, V1, and this vector, V2. And I'm asking what is the span of these 2 vectors, V1 and V2. I'll repeat what I said before. The span of V1 and V2 is the set that contains V1 plus V2, contains also V1 minus V2, V1 plus 30 V2, 3.8 V1 plus square root of 2 V2, and so on. It contains all linear combinations of V1 and V2. Right. How does it look like? How does this set look like? I'll do my best to represent it properly. This set is, imagine here we are taking a surface that contains, like a flat surface, a plane that contains these 2 vectors. So you see I'm doing my best. I'm not sure I can do it. Maybe I can show you with my fingers. So these 2 fingers are the 2 vectors I talked about. What is the span of my 2 fingers? It is a plane that supports these 2 fingers, that is supported by these 2 fingers. It is the plane that contains these 2 vectors, a plane that contains them. Okay, it is not this, it is not this, it is exactly this. I'll show you like this, my 2 fingers and the plane that contains them. Now, what if I take 3 fingers, this one, and this one? What is the span of 3 fingers, like this? It is the whole 3-dimensional space, because there is no flat surface that contains all 3 of my fingers, at least the way I have put them like this in space. But what if I take 5 fingers, let's say, and I keep them flat? I take 5 fingers and I keep them flat. Then there is a surface that contains them. This is the span of my 5 fingers. And if I put this down, if I put my thumb down, what is the span of my 5 fingers now? It is the whole 3-dimensional space. In other words, it is the smallest vector space that contains my vectors. So maybe this is worth taking a moment to write down. The span of a set A, the span of a set A, is the smallest vector space that contains A. And let's take a moment to elaborate on that a little more. So the smallest vector space means that if a line can do the job, it's this line. If you use one finger, there is a line that supports this one finger, this one vector. This is the span. If I have two fingers, like this, parallel to one another, if there is a line that does the job, use the line. That's the smallest one. Don't use a plane, use a line. If my two fingers are like this, then there is no line. I have to use a plane. I have to use a plane. This is the smallest. This is the smallest set. This is the span of my two fingers. If I use three fingers and they are on a flat surface, I think you got it. I shouldn't repeat it anymore. But as I said last time, these things, these concepts in linear algebra can sometimes be a bit abstract. If anything is unclear, you shouldn't expect from these videos to clear out all your doubts and explain everything to you perfectly 100%. If you have any questions, you come to class and you can ask your questions and we can discuss. That's why we have these weekly meetings. Then linear independence. I think there is a little bit of a delay. There is the slide. Lovely. So let me state this problem, this question. Take V to be a vector space and take a selection of vectors, V1, V2, V3, like the fingers I showed you before. And then I'm asking what is the span of these vectors. So I have denoted this by A, big A. Big A is the span of V1, V2 up to Vn. And I'm asking now, if I remove one of them, let's say the last one, and I get a new set, A prime, which is the span of V1 up to Vn minus 1, is it possible at all that nothing changes? Is it possible that taking out Vn doesn't change the span? Or to put it differently, is it possible that Vn is not necessary to define the span? Example, three fingers, all in parallel. What is the span? What is the smallest linear space that supports them, contains them? It is this line. So if I have two fingers, did I need the third one? No, I didn't. It's still a line. The third one was redundant. Take out another one. I have a single finger here. Okay. Maybe I should be doing this. I have a single finger. Here is the line that supports it. So one is enough. I didn't need three. Again, take three fingers like this. Okay, these are together. This is not in parallel. What is the smallest set that supports them, that contains them? It is this plane. If I take out this finger, I have only two vectors. What is the smallest plane that contains these vectors? Again, the same plane. Nothing changed. So this was redundant. So this can happen. This can happen that you have redundant, unnecessary elements in a set. And if you take them out, they give you exactly the same span. Next topic, actually an example on what I just presented. Take three vectors, V1 and V2, and take V3 to be the sum of V1 plus V2. V3 is V1 plus V2. And then take the span of V1, V2, and V3, and I'm asking actually whether I need V3 at all. So let's write out what the span of V1, V2, and V3 is. This span is the set of all linear combinations. So it is C1Y1, C1V1 plus C2V2 plus C3 V3, where C1, C2 and C3 are numbers. Now, if I replace V3 by V1 plus V2, C3 we said is V1 plus V2, and then I can make a few algebraic manipulations. I can see that Y is equal to a number, C1 plus C3 times V1, plus another number, C2 plus C3 times V2. So, to put it simply, this is the linear combination of V1 and V2. Indeed, if you define A1 to be C1 plus C3 and you define A2 to be C2 plus C3, then you can write the span of V1, V2 and V3 as the linear combination of only, we see it here in the last equation, as the linear combination of only V1 and V2. A1 V1 plus A2 V2, which is what? It is the span of V1, V2. So what I'm trying to say here is that we started with 3 vectors, but the third one was redundant. We didn't need it to be there. And this brings us to the concept of linear independence. So take V to be a vector space as before. We ask, given some vectors v1, v2, v3 up to vn, we ask whether we need all of them. Do we need all of them to define a span? If we need all of them, then we say they are linearly independent. We say in particular that they are linearly independent if this equation is satisfied. Lambda 1 v1 plus lambda 2 v2 plus lambda n vn is 0 can only happen if all the coefficients are 0. Why is that? This looks like a strange statement. If they are not 0, so let's say that not all of them are 0, but instead you have lambda 1 v1 plus lambda 2 v2 is equal to 0, and lambda 1 and lambda 2 can be taken such that they are not equal to 0, but this is satisfied. You know what happens then? Then I can write v1 in terms of v2 like this. This is equal to minus lambda 2 divided by lambda 1 times v1. I can express v1 in terms of v2. v1 is a kind of linear combination of v2 already. Sorry, this should have been v2 here. v1 is a linear combination of v2. It is a number times v2. So I can simply get rid of it. I can eliminate it. v2 suffices to describe linear combinations of v1. So I don't need it. So that's the meaning of linear independence. It says that if a linear combination is 0, the only way for this to happen is for all coefficients to be 0. Why? Because if not, then I can solve for one of these vectors in terms of the other vectors, and I can express one of these vectors as a linear combination of the other ones. So I don't need it to describe spans, to describe linear combinations. So this is the concept of linear independence. I think we'll stop the video here, mainly because I want to restart the recording, because apparently there is a little bit of a delay. It's a technical error. I don't know why this is happening. And in the next recording, we'll move on to the concept of basis and dimension.